Now we need to change directory to the location of our repositories. So what I'm going to do is go to the LoopStructural workshop. I'm going to copy that path and I say CD and change directory into that location. So you can see here that it says Loop Workshop, which is the workshop environment. We then have the path to my LoopStructural folder. And then I'm going to start a Jupyter notebook by typing this command. So the Jupyter notebooks are an interactive way of running Python's running a Python interpreter, and it allows you to run sections of code and see the output as you're running the code. So it's quite useful for building up an example and looking at the data sets. And you can also add in markdown text so that you can see what the notebook, what you can add in some user guides. So we're here, we can click on the Start Here notebook. And there are 5 notebooks that we can go through. So just a quick overview. The first notebook is basically building a conformable horizon using LoopStructural. We can use different interpolation algorithms. We can vary some of the parameters in the interpolator and look at how to do some basic visualization. The second example is an application of our fold interpolation. So we use the structural geology of the fold, so looking down plunge of the fold to constrain the geometry of the fold, and then add these constraints into our implicit interpolator. We do a comparison with classical methods. So if you're able to get SURFy to work, you can compare our radial basis interpolator, discrete interpolation, and our fold interpolator. So we can see how different they'll look. The third example is a polydeform fold, so where we're trying to model a refolded type 3 interference pattern using the fold constraints. And the fourth example is a faulted intrusion. And then the fifth example, we use the map to loop library to generate a data set of an area in Western Australia. So in this example, we're looking at the Turner Syncline in the Hamersley province. And we then extract all of the data using map to loop. So we extract the base of every unit, we extract the fault geometries, we interpret what we think the fault displacement is, we work out what the ordering of the different units within a stratigraphic package is, then we build up an input data set for 3D modeling and generate a model. And so the LoopStructural part of this code takes about 5 minutes to run, and the map to loop probably takes about 5 minutes. So we're able to create a regional geological model in 10 minutes, and it varies depending on the data sets, the size of the area obviously we're looking at. I tried it the other day on a 100 by 100 square area, and it took about half an hour, which on a basic laptop is not too bad really. So whilst you're here, if you want, you can have a look at on GitHub for LoopStructural. If you are at all interested, if you use it, please give LoopStructural a star. It really helps in building up the recognition that the library is being used. And I have a mailing list here, so you can sign up to it. And if I do any releases, I'll post that in the mailing list. And you can follow Loop on GitHub. So let's get started with the first example. So we can click this link and it should open the first example 1 notebook. And in this example, we have, so there's a little bit of a text to say what the tutorial is doing. So basically it's explaining implicit modeling. We're going to start off by defining the inputs that we need. So we're going to import the geological model from LoopStructural, which is our main sort of entry point to creating a model. It manages all of the interpolation, assigning the data sets and all that sort of thing. We'll then import the LavaView model viewer so that we can look at the model that we've created. So this is an interactive 3D viewer within our Jupyter Notebook environment. And we have a demo data set, which is the Claudius data set. And then there are a couple of other libraries that we need. So pandas and NumPy are required. So we can run that cell. So if you haven't used Jupyter Notebooks before, you can either run the cell by clicking run or shift enter. And the way that this works is it will create a kernel, which is an instance of Python that has all of the variables that you're using. So it's basically like if you ran a Python command, but then you opened an interactive interpreter in Python and you never actually closed it. So all of the variables that you make, unless they're overwritten, will stay active. We have a Jupyter Notebook here, so we can run the cells by clicking Shift Enter or the Run button. So let's run the first cell. And this take a little while. We have to import the required libraries. The next cell is loading the input data. So we basically load a pandas data frame with data and then the bounding box, which is the origin and maximum. So we can run this, and then I'm just going to insert a tab below, and then we can have a look at what data is. So data is a Excel table basically, or a CSV. So we've got X, Y, Z, the value, so that's the distance to the reference horizon, and then the name of the feature that we're trying to model. And then we've got NX, NY, and Z, which are the normal components to the vector. And so then we have BB, which is the bounding box. So we can have a look, and we've got two vectors, which are the minimum and maximum extent, or the origin and the maximum extent. So the next cell, so I'm just going to delete that. So the next cell, we want to create a geological model. So our geological model is the object that manages the location of our data points, assigning which data points to which scalar field. We rescale the data points so that they are within a local model coordinate system. So this is using the origin and the maximum extent. And then it works out what type of observations we've actually got to determine how to assign these to the interpolator. So we can do this by creating the model using the bounding box. So giving it the origin and then the maximum. So we run that. And then this is just showing the data that I showed you before. So just to visualize what we're actually looking at, we've got the two data types basically. We've got data types that have a value and then data types that have a vector. So I'm going to create a 3D viewer using LavaView, and then I'll add the value data by finding the observations that the val is not nan, and and assigning these. So the syntax is we have a vector for a matrix for X, Y, Z, and then a vector for the coloring field. Now it's missing a keyword here. We need to specify which color map. So we can say CMap is rainbow, which is just a standard-ish geological color map, but we can choose any matplotlib color map. So we can run that, and that will create a 3D viewer, which is interactive. So we can actually turn that around by holding the left mouse button and spin it. We can press the right mouse button to move the viewer around. The wheel will zoom in and out. And you can rotate the model by holding the middle mouse button and moving the mouse around. So a cool sort of attribute of the viewer is once you've found an orientation that you like, you could create a variable called rotation, or viewer underscore rotation, and make that equal to viewer.rotation, which is an attribute that extracts the current view rotation of the viewer. And then if we create a new viewer, we can actually just assign it to this rotation. So rotation is just a vector. rotation, and that is a vector that's just got 3 degrees, so basically the different rotations. So to create, we'll come back to that in a little bit, but to create a geological model, we want to assign the data to the model object, and we can do this using the function that is setModelData. And this basically goes through and it adds in any columns that are required by LoopStructural. It converts from strike and dip to normal vectors if it's in normal vectors. It will rescale the data points to the right scale, and various things like that. So we assign our model data, and next part is how we add a scalar field to our model, or how we assign the stratigraphy observations to the stratigraphy geological feature, which is a conformable foliation, so bedding. So we can do that as simply as creating a variable, which is strati equals model.create and add foliation, and then strati. So we can get rid of all of these. So I'll just, I'm just going to comment them out. So you can do that shortcut with command \, and that toggles commenting, and we will run this. And so this uses the default parameters, which is the piecewise linear interpolator, with a, I think, either 10,000 or 100,000 elements, and the conjugate gradient solver. So we can have a look here to see what at the documentation to see what the default parameters are. So if we were to look at the model and then we go create and add foliation, doesn't say, so we want get interpolator. So we're using PLI with 100,000. So going back to this, and so it's finished running, there's no star there. Then we can use the visualization library. So this is viewer, so same sort of syntax as before. And what we're going to do is assign it to the model, so we know the bounding box of the viewer that we're interested in. Set the background to white, so if we were running it in a, you can set it to whatever color you want. And then we're going to pick out the unique values so that we can create surfaces for all of the places where we had observations of the scalar field. And then we can add ISO surfaces, and we are going to add them using the model.feature0, which is the first feature in the model class, or strati, which is the same thing. We're going to color them by this scalar field, and we're going to use the prism color map. We're going to add a scalar field, which is basically the block, and we're going to use the prism color map there as well. We're also going to add the data, so using the feature, and then there's a couple of flags to say that we're going to add gradient data, and we're also going to add value data. These don't actually have to be included. You can not include them. And then here I've assigned the rotation to be this vector, but what if we do viewer underscore rotation? It should use the rotation from our previous viewer. So we can run this. And there we go. So we have our scalar field, and it is showing the ISO surfaces. We can have a look at how well it worked, and it looks pretty good. Now, so one of the design sort of concepts that I had with the visualization was to use a very similar syntax for all of the different types of features that we're adding. So, for example, if we're adding a an ISO surface, we can add an ISO surface simply with viewer.add_ISO_surface and specifying the feature. And what that does is it finds the average value of the geological feature within the model area and adds that ISO surface, and we'll color it red, so giving it a specific color. We have the same syntax for adding a scalar field, where we just have to add the model. And then there are all these additional keyword arguments that can be specified to customize our plot. So we can specify the color map to be prism. Here we're doing the same thing, and we're saying that we want to paint the feature, so paint the surfaces with the value of the surface. So basically it's coloring the different ISO values by their relative colors. And we want to specify that we want an ISO surface at the unique, which are this vector of unique values. And you can see that the data points have also been added, so we can turn these on and off as well. And if you want to, you can add in some keyword arguments, so changing the point size, or we can actually change these attributes within the panel for lava view. So if you wanted to change the size of the points, we can just use this, and that will change the points to be a lot smaller. So the visualization is fairly intuitive and quite quick, and yeah, there's a very basic example. Now the default viewer uses a cubic, so the same number of elements in X, Y, and Z for ISO surfacing. Now if you wanted to change, so this basically viewer.end steps is using the end steps variable, which is using 40 by 40 by 40. So we have 64,000 elements. So viewer.end elements. So viewer.end elements, we can actually set that. So rather than setting end steps, and we could say, let's make it 1E5. So that's just a little bit higher resolution. Actually, we'll have to do it here. So viewer.end elements equals 1E5. And get rid of that extra bracket I put in. And so this will ISO surface on a finer grid, but also when using the specifying with n elements rather than n steps, it actually makes sure that the cells are cubic rather than having the same number of elements in X, Y, and Z. So this should be a slightly better drawing of the ISO surfaces. So that's something that I will actually change in the future, is changing from using the n steps to just using n elements and having the option of specifying n steps rather than starting with n steps. So I think that's the basic introduction to LoopStructural. So now we could have a look at the next example. So if we're going to go to the next example, we're looking at how to model a fold. So if we open up this example, we need to have the IPython interactive widgets, so ipywidgets, because in this example we're going to change the number of data points we're using. So we have similar sort of thing here with with the imports. So we're importing geological model, we're importing a knotty single fold example, and we're importing the lava view model viewer, but we're also going to import a rotation angle plotter as well. And there's a couple of utility functions. So we can run this, specify our imports. We'll run the next cell, which is importing the required modules for the interactive plots. So this is just an overview of how we model folds. And so basically what we do is we construct a structural frame. So what I was talking about before, what I've talked about with So we construct a structural frame, which is a curvilinear coordinate system that defines the structural feature using the main structural element and then a structural direction and an intermediate structural direction. So in the case of folds, we're using the axial surface and the fold axis, and we characterize the geometry of the fold around the axial surface looking along the fold axis. So, and then we can add these constraints into the implicit modeling, into a discrete implicit modeling framework. So we can load the data points, and you can see here that we have some value data points, some orientation data points with strike and dip. They're all for a feature called S0, and there's a random variable, and the random variable is so that we can sort this data frame and slice the data frame, so only extract the first, say, 10 or 50 data points, but we'll always be extracting the same ones. So we also want to add in an additional data point, which is a value constraint, so that this is basically saying that at this location we want the scalar field to be 0, and this is just for our interpolator. So let's have a look at what the data points look like. So this is just the orientations. So they're getting converted into, oops, I need to run the cell before for it to work. And the cell before that. There we go, so too busy talking and I forgot to actually run the code. So here we can see that we have got some normal vectors. So remember, we're looking at normal vectors here. So our folded surface would be perpendicular to the normal vector. So we're looking at a fold that, if you're following my cursor, will wrap around and around and around and around and around and around and around there. And so a probably tightish fold. And obviously we're not looking at any contacts, so we can't judge the amplitude of the fold. But for reference, the data that it was sampled from is this fold here. So the first step, what we're going to do is we're going to compare using the PLI, so piecewise linear interpolator, and SURFy interpolator for varying number of data points. So we can just run this cell and go back up, and we can see there's two sliders here, two interactive toolboxes. So we can choose the number of data points. Now I'd say start with about 20 and run the interpolator. So this is basically building a geological model, adding the data points, doing the visualization, and you can see here that we have a few surfaces that have been plotted, and it's fairly open, doesn't really seem to be capturing the second fold hinge over here that we were seeing in the data points and also in the reference model. We could have a look at how well SURFy does. So remember, SURFy is a data supported interpolator rather than a discrete interpolator. So it should fit the observations better, but it may blow out more away from the data points. So if we want to run that, we can see that SURFy actually does a much better job when in this example, and it's kind of what we would expect because we've actually got quite a reasonable coverage in our data points. Now, if we wanted to drop the number of data points down, we could go to, say, 11. And SURFy is still doing a pretty good job. I'm just going to change the slider here to 1. So this here is saying that we want the number of points to go between 1 and 200, stepping at 1. So I want to look at what happens when the number of points is, say, 4, and we use SURFy. And we can see that obviously we're going to be missing most of the information because we're only capturing a couple of data points in one limb. So as we increase the number of data points, we will hopefully become closer and closer to capturing the actual geometry that we're expecting. So at 8 data points, we're almost getting that second fold hinge. And I think if we go up to 10, we're probably going to get there. Now, if we use the discrete interpolator, it will probably not work because it's really trying to minimize the curvature of the surface more than what Surfy does. So if we have a look at that, you can see that the discrete interpolator really misses that second fold hinge. Now, that this example is probably not the most representative of a real case study, because what we've actually got here is data points that are spread throughout the whole model volume, and also in the Surfy example, they really were, well, in both examples, we've got the data points that are actually covering the model area quite well. So if we only had specific outcrop observations, I think you'd find that there'd be some more issues in how the interpolators perform. But you can basically see that as we decrease the number of data points, the ability for the interpolator to actually fit the structure that we're expecting decreases, and that's because it's missing some of the geological knowledge. Now we can go down here, and this is just a bit showing how we incorporate the geometry of the fold. And what we can do is run the fold interpolator, and this uses very similar setup to before. We specify we use 10 points, and so this builds a fold frame, then characterizes the geometry of the fold around the fold frame. Then it will interpolate the scalar field for bedding using some additional constraints that were found by fitting the geometry of the fold looking down plunge fold. So we'll have a 3D model and a picture of an S-plot, which is basically the angle between the folded foliation and the fold frame. So here, and you can see that in this example, where not only are we capturing both fold hinges, we're actually really capturing the tightness of the fold, whereas when we were looking at the previous example with the discrete interpolator, we were not capturing any tightness. If we run it with Surfy, we do get the folding and we get the second fold hinge, but we do kind of miss the tightness of the fold. So if we were to add more data points, and I'll just go to 55, then we should really be capturing the geometry of the fold. So you can see here, this is sort of moving more towards the model down below that's using the fold constraints. So just by adding in an extra sort of some more structural geology into our modeling, we're able to capture the geometry of the folded surface much better. So just something to think about is, do you think that a typical structural geology map and cross-section actually has enough data to be able to constrain the geometry of folds in 3D? So what I would be really thinking about is, when you're looking at these examples here, how much coverage do we actually need to be able to capture the geometry of the fold? So in the next example, we will look at using modeling refolded folds. So this uses the fold frame for multiple folded for multiple folding events. So we use a similar sort of thing. We'll import the observations, define a data and a bounding box, and I just do a little bit of pre-processing of the data here. But to start off with, we'll model the fold frame for the most recent foliation. So this should be reasonably smooth. So we don't use any fold constraints for this. We just run it using normal interpolation. And so it does give you a warning here saying that the constraints can't be added for coordinate 1, but in this case it's okay because we're not actually modeling the geometry of the fold axis, because we know that it's a type 3 interference pattern. So this is a little bit of a synthetic example, but it is nice. So here we have the scalar field of S2. Now we can model S1 because S1 is folded around S2. So we use the S2 fold frame, calculate the fold rotation angles, fit a Fourier series, use the interpolator to build another fold frame. So do this. And then below we have our S-plot, and the S-plot is basically showing the geometry of the folded foliation looking down plunge. And just wait for that to run. Yep, so there we go. And if we want to have a look at what the 3D model looks like, there we go. Now we can use this S1 fold frame to model S0, and so we're applying the same step where the rotation angle of between S1 and S0 is calculated. We fit a Fourier series to this, use these constraints to model S0, add them into an interpolation, and so it's a little bit backwards in how it's shown in the code, because what actually happens is we calculate the rotation angle between S0 and S1, and then this gives us the this plot here, and then we use these data points and this S variogram. So the S variogram actually picks the fold wavelength. So the first maximum of this is the half wavelength of the fold, and then we fit the Fourier series to these observations using the wavelength guess, and then add this. This adds constraints into the implicit interpolator that then are used to build the final fold frame. So I showed the plot afterwards just to show what has happened, but actually all of this happens automatically. And we can then have a look at what the folded scalar field looks like. And you can see that we have a refolded fold. So here is the S0 scalar field, and you can see that if we were to trace out these hinges between these folds, it would be looking similar to what the S1 foliation looks like. And you can see the surfaces here. So it is a little bit of a it's a nice example showing how the refolded folds work on and yeah. So let's move on to the next example, which is adding faults into the interpolator. So what I want to start with is just a bit of a point about how faults can be added into implicit interpolators, and that's using a step function. So a step function is basically saying that as we move across the fold, we're going to change the scalar field by this amount. So it doesn't add any concept of kinematics in, and so as a result, we can get faults that don't actually look like what we'd expect. But really, we only see this happening when we're adding a fault to a surface, to where the angle between the fault and the faulted surface changes. So this has happened where you're modeling an intrusion, or where we're modeling a fold series, or where you're modeling a listric fault, where the fault would have a high angle with stratigraphy and then decreases to a low angle. And where you decrease to a low angle, you may not actually get the displacement that you're expecting. So just to try and highlight that, here is a really sort of a schematic of adding a fault to an intrusion, and the intrusion is just a spherical function, and where our fault frame is just, our fault is saying that above 50 there's a strike slip fault. And you can see here that we're actually just shrinking the intrusion on one side of the fault. So not necessarily what we expected, although it could be okay if we had different kinematics. So what we do in LoopStructural is, rather than adding a step function or trying to modify the way the interpolation actually occurs to incorporate discontinuity, what we can do is use the fault kinematics to actually unfault the data points and interpolate a continuous surface. So basically, we're using the same steps as before. We build our model, assign an origin and maximum, set the model data points, and then we can create a fault frame, assign a displacement, and yeah, and so these unfault the points. So what I've got here is just a fault, and then I'm going to show you how the fault would actually unfault the data points, so the direction of unfaulting. And then what I want you to do is just have a play around with the interactive widget to see what displacement you'd need to minimize, to unfault the data points, and then we can add this into the description of stratigraphy and have a look at what yeah, so here we have, so I guess, so here we have a fault surface, our restoration or our strikes, our fault slip direction, and the location of the data points on the hanging wall of the fault. And so these so what I want you to try and do is minimize this displacement. So we can try what happens when it's 200, and you know that the answer is 500-ish. So we can see that we've almost created a sphere. So basically, we're trying to minimize the difference between the hanging wall and the full wall. So our displacement's 500. We can add that there, and then we can add the fault to the implicit surface. And here we go. We have we have our data points, our fault surface, our data points, and then our ISO surface of the intrusion contact. And so you can see that we haven't shrunk the volume of the intrusion across the fault.